Welcome to BYJU'S exam prep, and I welcome all for this particular session of NIELIT 2023. Hi sir, Sumashriya, welcome to this session. So in this NIELIT 2023 YouTube sessions, I think we already completed few subjects. So now today I am going to start with data structures. There will be 3 sessions for this data structures, my dear friends. So today I will be discussing about problems on linked list and arrays together with the basic concepts. Okay. So in this particular series we will discuss both basic concepts as well as problems. Okay. So day after tomorrow again I will come up with stacks and queue and one more session for trees. So that will generally conclude your data structures topic. Okay. So without wasting much of your time, let me start with today's session, sir. And before starting the session, this is about me, myself Sridhar Dhulipala, having, hi sir Aditya Agarwal, very good evening. I'm having 20 plus years of teaching experience and I'm associated with BYJU'S from past 2 years. So under BYJU'S exam prep app, those who are preparing for this NIELIT, you have one news, like under BYJU'S exam prep app, we are having the video lectures, recorded video lectures. See, they are the videos which were prepared in a visualized animated manner, first of its kind, and with BYJU'S you are having this double advantage, like both recorded as well as live content. Okay, so you can find the following subjects which were recorded by me: engineering mathematics for all the branches, whereas for computer science students exclusively discrete mathematics, algorithms, C programming and data structures. Okay, you can join my Telegram group CS_Sridhar for regular updates about my classes and of course even for this NIELIT updation, my dear friends. Okay, so let us start with today's session, my dear friends. So arrays and linked list. Am I audible, visible to all of you? First of all, is my voice clear? My audio, video, everything is fine? Hope you are all able to hear me clearly, right? Yeah. Okay. First of all, if you observe, see, for one dimensional array, so it is a collection of elements which can be indexed by a particular index, my dear friends. Okay, so the elements are stored in contiguous memory locations. So you can call an array as a physical storage, my dear friends. Am I clear? And if you consider the array indexing formula for one dimension array, see, generally C array starts with index 0, but generally if you talk about arrays, the indexing may start from L and it may go up to U, LU. Okay, so suppose this is your array LU, where L is the lower index and U is the upper index. So the question which can be asked is size of the array, that is upper bound minus lower bound plus 1, or upper index minus lower index plus 1. If you do it, you are going to get the size of the array. For example, if I am having an array of size, array say from 5 to 15, the size of the array, that is number of elements in the array, is given by 15 minus 5 plus 1, which is nothing but 11 elements are there in this particular array. Hi Sayal, how are you doing? Then there is something called indexing formula. See, my dear friends, suppose if alpha is the base address means the starting memory location address. You know the starting memory location address is say alpha and you also know the size of each element. Suppose size of each element is say W. This is the size of each element. And if you want to know the location, or I mean for a particular index, if you want to know the location, you can use this indexing formula, my dear friends. Okay, so base address plus I minus L into size of each element will give you the location of ith index. Location of ith index starting from lth index. See, my dear friends, for C arrays the story is very simple. For C arrays the story is very simple, because in C arrays what happens? Location of AI if you want, Starting memory location address is obviously address of A0 plus I minus lower index will be 0, so I minus 0 is I only into size of the element. So directly you are going to get the address of ith index using this particular formula by reference. Address of ith index using this particular formula, we can easily get it. Am I clear? And you can also extend this for two-dimensional array. So here I am just giving it for C arrays. Of course, this indexing formula, column major order, maybe for any other programming language, my dear friends, because hopefully you all know it. In C language, the two-dimensional array is stored in row major order. It is stored in what order? Row major order. That is first row, second row, third row, like this, row by row. See, even though logically it is a matrix, but physically the elements are stored contiguously. See, when you want to store contiguously, you get one doubt whether you are going to store first row, then second row, then third row, like that, or you are going to store like first column followed by second column followed by third column and so on. So if you store row by row, that is called row major order, and if you store column by column, that is called column major order. And in C language, the two-dimensional array elements are stored row after the row, that is row major order they are going to be stored. Is that clear? So this is the indexing formula for C language, sir. C 2D arrays. Of course, you can also write the same formula for column major order. The formula is very simple. Address of 0th location followed by I. Suppose if lower index is L or L1, you can say I minus L1 into C. C is number of columns. Plus J. Or if you are having this index as some L2, then you can say J minus L2 into this K. Here K is taken as size of the element. And if you want to do column major order, it would be J into R or J minus L2 into R. R means number of rows plus I minus L1. But luckily here it is 0, so I directly into K, where K is the size of the element. So I can use this formula to get the answers very quickly, my dear friends. Hope you understand. Yeah. Please answer this question. Which one of the following is a physical data structure? Array, linked list, stack, yeah, tables. You can say hash tables also, my dear friends. Physical data structures means, see, my dear friends, we'll study linked list little later. Okay. In linked list, see, logically they are stored one after the other. If it is a linear linked list, logically the elements are stored one after the other. Okay, logically they are linear, but physically they are not linear. Whereas array, physically, logically the elements are linear, my dear friends. So which one of the following is physical data structures? Okay, it was a question asked in UGC net. So array is the answer for that. Am I clear? Sir Malik, it is array, my dear friends. Physically, it is stored as an array only. Physically, it is an array. Hash table again depends on the indexing, my dear friends. Okay. So generally, the answer for this is array. The next question. Suppose you are having an array where the indices starting from -7 and going up to 3. It is stored in the memory. Each element of the array occupies 4 bytes. The starting location is given as 2500. That is, starting memory location address is 2500. And each element of the array occupies 4 bytes. That is size of the array element. You can say K or W, sir. Size of each element, which is equal to 4 bytes. Size of each element is 4 bytes. Now he is asking what is location of A1. See, the formula for location of AI is equal to base address plus I minus starting index into size of the element. Here alpha is 2500. The value I, first index you want, minus L Okay, sorry for that. L is -7 into size of each element is 4. 2500 8 into 4. Very good, Sumashreya and Shyam. Super. Joshna, very good. So the answer would be 2500 plus 32, that is 2532, which is option B. You are rocking. Perfect answer. Next question. Now I taken a two-dimensional array. So the two-dimensional array is stored in row major order and each element occupies 2 bytes. And the starting memory location address is also given as 1000. Now he is asking what is the location of A to 10, my dear friends? What is the location of A to 10, my dear friends? Same story. You want location of Aij in row major order. That is very important. Whether you want it in row major order or column major order is very important. So the answer would be starting base address I, because the base, this starting indices are zeros, C array, so I minus 0 you can directly do it, into what happens, because when you want to cross that particular ith row, you want to go up to ith row, first rows you have to complete in each row, this many elements will be there, number of columns. So we should know number of rows. The number of rows would be 15 minus 0 plus 1, that is 16. The number of columns would be 20 minus 0 plus 1, that is 21. So I into number of columns plus j into size of each element, either W or K you can write it. So base address is 1000. Starting index, I mean you want A to 10, you want location of A to 10. This is 2 into columns, that is 21, plus j value is 10 into size of each element, which is 2. Super, very good sir, you people are rocking. So the answer for this problem would be 1000. This is 42, 52, 52 into 2, 104. That is 1104, option C. Super. Please answer the next question, sir. Very good. Some people are answering really good. Very nice. Which of the following is true for computation time in insertion, deletion, and finding maximum and minimum element in a sorted array? So here we are having a sorted array, sir. That is, the array is a sorted one. The array is a sorted one. Okay. So sorted array. So in this, the elements are stored in a sorted manner, my dear friends. Elements are stored in a sorted manner, my dear friends. Okay, very good, sir, very good. So when the elements are stored in sorted order, if you want to make any insertion, first of all, you have to search for that particular element. First of all, you have to make search for the element. Now, some people say that, sir, I do binary search. Wow. You can do binary search. But suppose the element is the first element. The element to be inserted is the least element. In that particular case, when you insert the element, remaining elements need to be moved. If you just need to search using binary search, you can get that position of the element in log n time. But if suppose in the worst case, if it is the first element, to accommodate that particular element, remaining elements need to be moved to the right. Then this element can be inserted. So that movement need the entire traversal of the array, so theta n. So the insertion in the worst case take theta n time. Same is the case for deletion. See, you can find the element in log n time using binary search, but for deletion and after that you have to move the element so that the array is a sorted array. It takes theta n movements of the elements. Okay, you just need to shift the elements to the left or right according as it is either deletion or insertion, my dear friends. But one interesting thing here is minimum and maximum. Minimum and maximum. See, if you are keeping track of what is the last element, last index where you are inserted, or how many elements are inserted, suppose if you keep track of that, if you just keep track of how many elements are inserted so far. So the first element is obviously the minimum because it is in a sorted order, generally means ascending order, sir. So this will be the minimum element, and whatever you inserted the last element, that is the maximum element. So if you can keep track of, whenever you do insertion, if you can keep track of the count, with that what happens, you can find last element, that is where the last index is there, you know it, there you can directly find the maximum element, and minimum element can be found in theta 1 time. So both of them can be found just by reaching the index. Minimum is obviously found in theta 1 time. If you can just keep track of number of elements inserted in the array, even the last element can be found in constant time, my dear friends. So the answer for this would be C. Very good, sir. Super. So now let us quickly understand the ideas of singly linked list, circular singly linked list, and doubly linked list, my dear friends. Okay. So I'll just quickly recap the idea about this linked list, my dear friends. See, in a linked list, we have the following node structure. This is the data field, and this is the link field. Is that clear, sir? So we are going to make this linear arrangement by links. That is, the links are going to create the linearity between the nodes, my dear friends. See, physically they are not linear, but logically they are linear, my dear friends. So initially you can just keep one pointer, which you can call it as, some people call it as head pointer or start pointer or first pointer or list pointer. Whatever name you want, you can give, sir, no problem. Okay, let us call it as a list pointer. Let us call it as list pointer. And initially this list pointer will be null, my dear friends. Initially this list pointer will be null. See, suppose you want to insert a new node, create a node whose data value, you can give some data value, say 15. Okay. See, once you create a new node, temporary node, okay, using dynamic memory allocation functions like malloc, you can create the node. Once you do it, the data field, because each fellow is having, suppose you call this as TMP node, temporary node. So TMP data you can update. TMP data is equal to whatever value you want to update, maybe 15 or some value. Then TMP link, initially you can keep it null. TMP link, you can keep it null, my dear friends. See, null means it is a null link, my dear friends. It is a null link. Of course, some people show null link something like this. That is your wish. You understand, it's enough, my dear friends, whatever way you show it. Now what do you want to do it? Because list is empty, you created a new node, you want to insert it. Directly you can say now, because list is empty, you can simply say list is TMP. By doing list is TMP, this new node will be inserted, my dear friends. So now your linked list would be what, sir? What is your linked list? This is your linked list. So anytime you want to insert at the end, okay, you can directly do it. Now let us understand different types of insertions. Okay, suppose you already have a linked list, my dear friends. Let me remove this story. Suppose you already have a linked list of few nodes. Suppose by some means you inserted. To understand the insertion at different positions, let me just show you a arbitrary linked list. Then we try to see how we can insert nodes at different positions. Suppose it is say 20, this is say 12, and this is say 18, and this is say 30. Now this is your linked list, my dear friends. Suppose you are having this particular linked list. Now let us see different insertions. So here I'll discuss three insertions. Similarly, 3 deletion options I am going to discuss. Very good programming, Bala. The first one is insertion at the beginning or the front, and insert at the rear or end, or insert at a particular position. See, my dear friends, let us understand insertion after a node. See, whenever you want to insert after a particular node, you have to traverse up to this particular node. Suppose you want to insert after the node 12, you have to traverse up to the node 12, my dear friends. So this traversal is required. So after this node, if you want to insert a new node, create a new node. Let us call it as TMP node. It may be having some data value, say 50. Now you want to insert this after P node. And in singly linked list, remember, whenever you want to insert, you should reach to the previous node. You should reach to the previous node of that particular node. That is, you want to insert at this particular position, you should have a pointer to the previous node, my dear friends. Okay, at this particular position you want to insert, you should have a pointer to the previous node. That is, you want to insert between these two nodes, you should have a pointer to this particular node. For that, you have to traverse from beginning till this particular node, my dear friends. Then what you can do? Simply TMP link is P link, then P link is equal to TMP. This is a common practice or a common method for insertion of a node after a particular node, my dear friends. Here there are two simple link manipulations, we can call it. That is, TMP link is equal to P link, and P link is equal to TMP. See, this pointer manipulation, what it will do? It will insert the node after that particular node P, my dear friends. Remember, you cannot reverse them. First, you can't do P link is equal to TMP. Suppose if you do this first, it is illegal, because if you do this first, you lost the address of the next node. You can never get the address of the next node. So this operation will make it what, sir? Suppose if you do this first and this next, the second one will do temp link will be like this, it will happen. Okay, so please be careful, my dear friends. The order in which the link manipulation to be done is also very, very important. Now, if you want to insert at the beginning, the story is very simple. You need to take a temporary node. The logic is very simple. Temp link, you have to do it is equal to list, and update the list equal to temp. With this, what happens? The new node can be inserted at the beginning. So this insertion at the beginning can be done in theta1 time, that is constant time. Whereas insertion after a node, okay, you have to traverse up to that particular node. This can be done in theta n time, because traversal is required means theta n time. In a singly linked list, traversal required means theta n time is the time complexity, my dear friends. And if you want to insert at the end, you have to reach up to the last node. That is, you should have pointer to the last node. Then you try to create a temporary node here, whatever value. Suppose here you can say 10, here you can say 60. So now what you can do? Simply P link is equal to TMP. P link is equal to TMP. Even insertion at the end will take theta n time, my dear friends. Am I clear? So in a singly linked list, if you want to quickly recap things, the traverse will take, yeah, search will take theta n time. The insertion at beginning, okay, so it depends where you are inserting. If you are inserting at the front or first, it will take theta 1 time, but remaining all, insert at position or end, you want to insert at position or end, it will take theta n time, my dear friends. So these are the common complexities one should definitely know, and especially for the examinations like NIELIT and all, they want to know whether you know the standard results or not. The questions are not that difficult for NIELIT examination, my dear friends. They are of same standard as BARC or ISRO examination. Some good questions are also there, and some questions are directly taken from GATE examination also. They are not complicated. You can easily handle them, my dear friends. Now, what about the deletion process? See, for deletion process, the story goes like this. let us consider your singly linked list, my dear friends. Here I am not writing the data values and all, you can just see that. See, if you want to delete the first node, it's very simple. Deleting first node is simply list link. That will do deletion of the first node. But it is always good idea to first make TMP is equal to list and properly delete this, my dear friends. Because in C programming, the memory delocation is responsibility of the programmers. Otherwise, there will be something called memory leak may happen. There is something called memory leak may happen. So please be careful, my dear friends. Am I clear? Then what happens? Suppose you want to delete a particular node. If you want to delete a particular node, we should have pointer to the previous node. Suppose I want to delete this node. You should have pointer to this particular node. Then what you can simply do? P link is equal to P link. So with this, what happens? Simply this particular node get deleted, my dear friends. Okay, and this particular deletion at a particular position, you need to traverse, therefore the complexity would be theta n. And similarly, if you want to delete the last node, same logic, sir. Reach last but one node. Suppose you have some more nodes. Suppose you want to delete the last node. You should not reach the last node, sir. You should reach last but one node. Then make the link of this equal to null. Make the link of this equal to null, my dear friends. That is very simple process. Am I clear? That is P link. Still P link is not null. You have to traverse. As long as the P link is not null, you have to continue traversing. Then you reach last but one node. Then you stop. Make the link of that P null. It deletes the last node. So here for deletion, the story is simple. If you are deleting the first node, just updation of the pointer is required, theta 1. Suppose they may ask you this particular question, sir. To delete the first node, how many link manipulations are required? To delete the first node, how many link manipulations are required? What is the answer? To delete the first node, how many link manipulations are required? Minimum link manipulations. To delete the first node, we require how many link manipulations? One link manipulation, no? Just one link. See, actually deletion always one link manipulation you can do it, but properly if you want to delete it, one more link you have to maintain. Not zero, Babu. One link you have to update this link, na? One should be there. First or middle or position, whatever it is, or end, you have to traverse. Therefore, it is theta. Right? Now, when it is a circular singly linked list, in a circular singly linked list, the story is something like this. You are having this linked list, my dear friends, where the link of last node is to the first node. And here, the point is, see, if you want to maintain a linked list, we should have a pointer to at least one node so that you can traverse it. And here there are two possibilities. Either you can keep the pointer to the first node, yeah, you can keep the pointer to the last node. Which one is better? Whether you should have a pointer to the first node, yeah, pointer to the last node. That's what we are doing, no? Head pointer to the next pointer. That's what we are doing, Sumashreya. See, the pointer manipulation is required, na? This pointer is to be moved. List is list next. You are doing, na? List is equal to list link. You don't call it as pointer manipulation. See, pointer is changed, na? Pointer is changed, na? There. Pointer is changed, na? Without pointer manipulation means how is it possible? Now, the question is, which pointer if you have, that would be better. See, for a circular linked list, generally the best pointer is the pointer to the last node. If you are having pointer to the last node, it would be better for you, my dear friends. Because if you are having a pointer to the last node, the insertion at the front and insertion at the rear can be done in constant time. See, insertion at a position is same as singly linked list. Insertion at a position is same as singly linked list. But insertion at the front or insertion at the rear can be done in theta one time if you are having the pointer to the last node. For example, if you want to insert at front or rear, there is a small variation for that, my dear friends. See, what you do is you create a new node. Okay, you can call it as temporary node. What you do is update the links of this fellow. That is, temp link is equal to last link, and last link is equal to temp. With this, what happens? This particular link is gone. Now, if you observe, last is pointing to TMP and TMP pointing to the previous node. And with this, what happens, sir? With this, what happens? The TMP becomes first node. With this, what happens? TMP becomes first node. So, if you want to insert at the beginning, you just need to do this, my dear friends. So, that is, you just need to do TMP link is equal to last link. TMP link is equal to last link, and last link is equal to TMP. See, if you just do this, let me call it as 1 and 2. It is same as insert front or insert at the beginning. But if you want to do the same thing, insert at rear end or insert at end, then also story is same. 1 and 2 you have to do it. That is, TMP link is last link and last link is equal to TMP. But after these two, you have to do one more thing, that is last is equal to TMP, so that this new node which is inserted becomes last node. So this is extra step required, my dear friends. This is extra step which is required. So for insert at the front, you require 3 link manipulation, whereas insert at rear, we just require 2 link manipulations. Insert at rear, we require just 2 link manipulation, whereas insert at front, we require 3 link manipulation, and this is the third one. This type of questions can be asked, my dear friends. This type of questions can be asked. Here you require just 2 link manipulations. Whereas here you require 3 link manipulations. And for circular linked list, circular singly linked list, or singular or singly circular linked list, whatever you call it. See, my dear friends, insert at first or last or end, whatever you call it. Okay, let us call it as last. Both will take theta one time. But insert at a position or middle, whatever you call it, for that you have to traverse, and that is theta n. And that is exactly same as insertion in a singly linked list, my dear friends. That is exactly same as insertion in a singly linked list, my dear friends. But what about deletion, my dear friends? Suppose you are having a circular singly linked list. I want you to please tell me what is the time, and I'm having the pointer to the last node. So please tell me, what is the time complexity for delete first node, delete last node, or delete at a position or middle position, whatever you call it? See, always remember, we need to have a pointer to the previous node. Then only this node can be deleted. That is the point. So insert first node can be done in what time? Insert last node can be done in what time? And insert at a position can be done in what time? I want the time complexities for these three, my dear friends. Please give me time complexities for these three. What happened? Are you answering, Babu? See, delete first node is very simple, sir. Just last link is equal to, that is last link is equal to, you need to delete this now. See, first node is very simple. You just need to make last link is equal to last link. By updating this last link to last link, that is this fellow will directly go to this. And this can be done in theta one time. But remember, if you want to insert at, if you want to delete last node, if you want to delete it, you should have pointer to this node. If you want to delete this node, we should have pointer to this node. For that, you have to traverse the entire circular singly linked list, my dear friends. Therefore, these two fellows will take time theta n, my dear friends. These two fellows will take time theta n, my dear friends. Next comes doubly linked list. So in doubly linked list, we have two pointers. One is previous and one is next pointer. You can call it as list pointer, which point to the next node, and the next node previous point to this node. The next node next will point to the next node, that fellow's previous point to this node. So this is what happens, my dear friends. So what is happening here? Every node will have two pointers. The next pointer point to the next node, whereas previous pointer point to the previous node. And of course, the first node previous will be null and last node next will be null. So here, please tell me, what about the complexities? Insert, first, last, and position. So obviously first node is very simple. We can insert at the first position in theta one time. But whether you want to insert at a position or you want to insert at the last node, you have to traverse it. So these two fellows will take theta n time, my dear friends. These two fellows will take theta n time, my dear friends. And what about deletion? What about deletion, my dear friends? Deleting first node, you are deleting last node, yeah, position. Okay, here there is one very interesting result. Okay, anyhow, I have a problem on that, so I'll discuss that. Deleting first node is theta one time because you have list pointer here. You can do it in theta one time. But if you want to delete last node, you have to traverse. You want to delete any particular node, you have to traverse. So it will take theta n time, my dear friends. It will take theta n time, my dear friends. Let us solve problems now. You are all ready? Quickly answer the questions, my dear friends. Consider the singly linked list. What is the worst case time complexity of the best known algorithm to delete the node A pointed to this node Q from the list? Okay, a singly linked list is given. Consider a singly linked list. What is the worst case complexity of the best known algorithm to delete a node pointed to this node Q is given. I think there is some statement, okay, statements are not given correctly, but the idea is you want to delete a node, the pointer to the node is given to you. The pointer to the node is given to you. Wow, Nishu Kumar, super. See, if you are having pointer to the node to be deleted, you can't delete directly. Because for singly linked list, you have to traverse up to this node. So you take a pointer and you traverse up to the previous node. Then you can do what, sir? P link is equal to Q link, you can do it. Then this node will get deleted, my dear friends. So the answer for this would be Babu Sayal Malik. Previous one is all order 1. You said that is wrong. Only first deleting first will take theta 1 time, but remaining all will take theta n time. Please note that. Careful. These are all simple things. Okay, we should master them. We should never forget them, my dear friends. Please note that. Got it? Babu got it. Okay, try the next problem. Consider the following linked list. Which of the following code insert node Q at the end of the linked list? So he given codes. You have to find out which code will actually insert the node Q at the end of this linked list. We are having list pointer. You have to tell me which code actually insert the node Q at the end of the linked list, my dear friends. Is the problem clear to you all? D. Aditi Agarwal, super. And Suma Shreya, super. Aditi Agarwal just saying yes sir. Okay, sorry. I thought she given the answer. Suma Shreya did given the answer. Good Nana, super. TV Suma Shreya, doing well. Properly understanding the idea. Nishu Kumar, super. Perfect. See my dear friend, what it is doing. See, the logic is first we have to take P is equal to list. As long as P link is not null, we have to move, that is P next. Okay, link or next, whatever. He is calling this fellow as next, my dear friends. As long as P next is not null, we have to move P to P link or P next. P next is not null, P move to P next. P next is not null, P move to P next. P next is null, stop here. Once P next is null, you stop there. See, there is a semicolon you see here. Now what you need to do, simply P next is equal to Q. See, such problems are very, very important for such examinations. Okay, especially like, NIELIT kind of examination. This type of questions are possible. Okay, may not be exactly same. Nana Manishankar Tiwari, C looks same, but if you say P is equal to Q, what happens? Only without linking, you are just making P is equal to Q. That will not link. Same linked list will be there, P becomes Q. That is wrong, Nana. C is wrong. C is wrong, Manishankar Tiwari. What happened, sir? Shiva Kumar, what happened? Why you are writing same answer 3 times when it is wrong answer? See, with this what happens? P becomes null. Then see, once P becomes null, P next. It is a wrong pointer manipulation. Okay, when a link null pointer you are accessing, that is wrong. Okay, so don't do that. Dereferencing null pointer you call it. That would be an error. अगला समस्या आपके स्क्रीन पर. Please answer. With regard to linked list, which null pointer dereference? Yes. Which of the following statement is false? which of the following is false? Super Sayal, perfect. So to search, it requires theta and time, that is true. This is true. To find maximum value, you have to traverse the entire linked list. That also true. So theta n is correct or order n is correct. The algorithm for deleting middle node of a singly linked list. See, middle node, if you want to find it, you have to search it. Okay. There is a slow and fast pointers. You can move it. With that, you can find middle node, which also can be done in theta n time, my dear friends. But deleting first element don't need order n operations. Even in the worst case, my dear friends, it is a false state. Even in the worst case, it requires order one time only. Okay. So this is very interesting, which I was talking about. Suppose you have this particular doubly linked list and you have a pointer to this node which need to be deleted. You have pointer to the node which need to be deleted. What is the time complexity for deletion of this particular node, my dear friends? Very good, Nishu, Sal Malik. Okay, okay, Sadhana, good. Everyone is saying that. See, actually, if you want to delete a node, we should have a pointer to the previous node. So you can just say Q is equal to P previous. So you can have this particular pointer. Once you have, you can say Q next is equal to P next. So what happens with that? Q next will be P next. Then P next previous. This is P next fellow, that fellow's previous. That is this link is given to Q. That is given to Q, my dear friends. So this link will go here. So with this, what happens? This node can be deleted and this requires just 3 link manipulations. And it can be done in order one time, my dear friends. It can be done in order one time, my dear friends. Super. Okay, next one. Which of the following is false for a circular singly linked list? With pointer to the last node. That is, we have a pointer to the last node. You have to tell me which one is correct. Okay, Nishu Kumar and Sayal Malik saying C. Insertion at the beginning requires theta one time. That is true. Insertion at end also requires theta and one time. That is true. Deletion at end. See, deletion at end, you can't delete this node because if you want to delete, you have to reach here. That means you have to traverse. So this is wrong. This is false. And he asked which one is false. C is false. Babu Manishankar Tiwari B gadu. C. C is the answer. अगला समस्या. Which of the following data structure enables us to delete the first and last element in theta one time in worst case, assuming we are given only a pointer to the list, only single pointer to the list. PDF नहीं मिल रहा है आजकल, देखेंगे. So circle a singly linked list with pointer to the last node. Sadhana, very good. Nishu, good. Aditi, Nana, check. Rakesh, please verify. Nishu Kumar, done, good. Manishankar Tiwari says C. See, my dear friend, if you are having circular linked list with pointer to the last node, deletion of the first node can be done in theta one time, but deletion of the last node, you have to traverse the entire linked list. Deletion of the last node, you have to traverse the entire linked list. So that will take theta n time. So this is wrong. Singly linked list, that is wrong. Because singly linked list, you have pointer to the last node. If you are having pointer to the last node, even the last node you cannot delete in theta one time. Okay? Nothing can be done in theta one time, my dear friend. Traversing also stopped there. Okay? That is bad thing. Actually, it is a, of course, you can just do this for, the purpose of stack or something like that. Okay? But that is also not a good idea actually. Doubly linked list with pointer to the last node. See, even if you are having pointer to the last node can be deleted in theta one time, but first node, if you want to delete, you have to traverse back. So that takes theta n time. So if it is circular doubly linked list, then this can be done, my dear friends. Circular doubly linked list, when you are having circular doubly linked list, this can be done in theta one time, my dear friends. So here, this fellow will have pointer of this, and this fellow will have pointer of this. So if you want to delete it, you can happily move to the previous node and you can delete it. If you want to delete this node, happily you can delete it. So both can be done in theta one time for this, my dear friends. So this can be done with circular doubly linked list with pointer to either first node, pointer to any node actually here. For circular doubly linked list, you actually can have pointer to the first node, pointer to the last node. Both can do this work. Even insertion can be done at the front or end in theta one time. Deletion also can be done in theta one time, my dear friends. Super. Consider a non-empty null terminated singly linked list with pointer to the last node. Consider a non-empty null terminated singly linked list with pointer to the last node. Which of the following set of statements is correct order to insert a node pointed by PTR? See, the idea is I want to insert that node pointed by PTR to this particular linked list, my dear friends. We only have pointer to that last node. Singly linked list where you are having pointer to the last node and you want to insert that PTR fellow. What is the correct answer, my dear friends? Sayal Malik says A. Same, no, all the three operations are same, only the order is different. I think B, D and C are same, na? D and C are same, I think. Okay, D and C are same, sorry for that. See, actually what we need to do, sir, simply make last next must be equal to PTR. Then PTR next you can make it null anytime. That PTR next can be made null anytime. But before making last is equal to PTR, we should do it. See, this last next is equal to PTR should be first, then last must be PTR. See, this fellow's order is very important. That PTR next null, you do it first or last or middle, it does not matter, sir. PTR next null, you do it anytime, it does not matter. But this fellow's order must be same. But if you do this first and if you do next, this is wrong order. PTR next, last is equal to PTR first, you should not do it, sir. This you should not do it before this. Please remember. Am I clear? Please note that, my dear friends. Hope you understand. Here is the answer. Super. See, last next is equal to PTR, then last is equal to PTR, then you can make PTR link is null anytime. The next one. Consider the following singly linked list with head pointing to the first node. What do the following statements achieve? So I given some code there. You have to tell me with that code what happens actually. With that code what happens, you have to tell me. What happened? Is it so difficult? P is head next, then head next is equal to P next. P next is P next next, P next next, and head next. This is head next is this fellow, sir. That fellow's next is taken to P. See, if you observe, head fellow is the first one. Head link is going to this particular third node. If you call it as first node, second node, and third node, and fourth node. Head next is going to the third node. Third node next is going to the second node. Second node next is going to the third node next. That is fourth node. So what is happened, sir? Second and third nodes are swapped by this. Second and third nodes are swapped by this. Super. Second and third nodes are swapped by this. Sayal Malik given correct answer. No one else attempted. See, this is where, the difference comes. See, basic results everyone remember. Nowadays, everyone remembers standard results. Maybe with that UGC net you can easily clear. But if you want to crack such competitive examination, little extra work, this kind of problems also we need to see. Am I clear? Of course, they are not very difficult. You should have the idea, concept correct. Am I clear? You can't remember such problems. See, for example, for a singly linked list, the the time complexities, you can try to remember them. For singly linked list, insertion at the first is theta 1, deletion at the first is theta 1, remaining all are theta n. Like that you can remember. Like that you can remember. But if he says, if I am having a pointer to the previous node of a node to be deleted, in how much time you can delete that particular node? Then you have to understand, then you can answer that question. In that case, it would be theta 1. If you are having pointer to the same node, to delete that in a singly linked list, you need theta n time. But the same story, if you apply it to doubly linked list, it can be done in theta 1 time, because in doubly linked list, you can go back to the previous node, then this can be deleted. So this kind of ideas, you need to apply properly. First, you should know the link manipulations basically. Okay. See, don't have to write exact code, but at least the links, how they are manipulated, you should understand, my dear friends. Am I clear? See, some people worry too much about, they are unable to write the complete code. See, at least minimum thing is, you should know pseudocode. Later on, some syntax you might be missing. You can work little hard to, make that syntax correct, my dear friends. But if you not even start that particular basic logic, if you don't have, you can't do the programming at later stage also. Please remember that. The last problem for today. Suppose we are using singly linked circular list without a head pointer and are using convention that list pointer L points to the last node. That is, it's a circular singly linked list or singly linked circular list, whatever you can call it. So this is the story we are having, and we are having pointer to last node. L points to the last node. L points to the last node. Now the question is, what this particular code will do? L next, this is L next, this one. So this is modified as L next, that is this actually pointing to this, we are making it point to the next one. L next, see L next, that is this fellow, is now L next, that is this. So it goes to this phase. So what is happening by this, sir? The second node is deleted. It would delete the second node. Very good, Aditi Agarwal. You are rocking. Super. Perfect. So that is the story, my dear friends. Hope you all understood the problems. Okay. So thank you very much for attending this particular session. We have 2 more sessions for data structures. And of course, on later stage, we also come and discuss about algorithms. But this week, alternate days, we are having this particular class. The same timing, sir, 10:15. I think 10:15 is mostly suitable for almost all the students. Okay. Thank you very much, Nishu. Okay. Good to see you back after long time. Good night, sir. Okay. So day after tomorrow, we'll discuss stacks and queues, my dear friends. Stacks and queues problems we'll discuss day after. That is on, today is 3rd, on 5th at 10:15 p.m. So please share this particular session with your friends so that they also. Next class I written Sayal, Shuma Shreya. Next class is on Wednesday, 10:15 p.m. Wednesday, 10:15 p.m. Okay, na? Shuma. Next class is Wednesday, day after tomorrow, 10:15 p.m. on stacks and queues. Okay, if you want, you can just revise those concepts and come so that we can take up problems. I'll just quickly review the basic concepts. Time complexities for insertion, the basic operations of stacks and queue. Okay, the circular queue basic operations. Then we take up mainly the questions which they are asking on this applications of stacks mainly. Those type of questions we'll take up. Okay, that's all for today, sir. Thank you very much. Keep